Okay, welcome back to Differential Calculus. I'm your tutor Ryan, and we are on part 4 of basic derivatives. We're going to continue with the polynomial section, which we are currently on, and we're going to move on to problem 3a now. Problem 3a is asking us to graph f of x and f prime of x, and then plot the tangent line to f of x, where the slope of the tangent line is 15, and then determine the equation of this tangent line. The last two parts are, I guess, one and the same. In order to do one, we need to do the other. So we're going to be tackling those last two parts at the same time. Okay, here comes the graph of f of x. Now that's just the graph of the original function. Here comes the derivative. It's a line, 24x plus 7. And just zoom out here a little bit to give you a better view of what it is that's going on. That's the function and its derivative. Alright, we're going to move on to the next portion of this. Okay, so in order to plot the tangent line to f of x, we're going to need the equation. So let's go ahead and find out the equation. We know that the slope is 15 for the tangent line. So let's go ahead and plug that slope into f prime of x. We're going to get 15 is equal to 24x plus 7. Now subtracting 7 from both sides of the equation, we get 8 equals 24x. And dividing both sides out by 24, we get 8 over 24, which is also a third. So now we plug the location of x equals 1/3 into f of x to obtain the corresponding y location of where the tangent line touches the function. Okay, so f of x, where x is a third, is 12 times 1/3 squared plus 7 times 1/3 plus 36. That 1/3 squared turns into a ninth. And then we're going to put everything with a common denominator of 9. That makes adding it all up much more simplistic. And the total of this result here is 357 ninths. Alright, so now we know the location where the tangent line touches the curve, and that's at 1/3 for x and 357 ninths for y. Alright, but there's a little problem. We need an equation for plotting lines in order to determine and then plot the equation of the tangent line. We only have a few things. We have a point for x, we have a point for y, and we have a slope. So, the equation of a line, when you only know the points, is y minus y1 equals m times x minus x1. Knowing the slope also helps, because it's a variable that we are going to need to know in order to substitute in. Alright, so we have all the variables on the side here, so we can move forward. Let's plug these numbers in. The result is y minus 357 over 9 is equal to 15 times x minus a third. Now this turns into y minus 357 over 9 is equal to 15x minus 5. Now let's bring the 357 ninths to the other side of the equation and collect like terms. The result is y equals 15x plus 312 ninths. We now have the equation of the tangent line with slope 15 that touches the function at xy equals 1/3 and 357 ninths. So we're going to go ahead and bring up the graph of the tangent line touching the point. The tangent line is in green. We can see that it's touching the curve at a specific point, although it's kind of hard to see from back here, but trust me, it is. We'll zoom in to give you a little better view. So we got the original function in red, the derivative in black, and the tangent line corresponding to the problem in green. Okay, so we've completed problem 3a now. Let's go on ahead and complete the example problem that I mentioned at the end of the third video. This problem stated, you change the position of your car constantly from 10 meters to 35 meters in 5.5 seconds. The derivative would be the rate of change of your location, which is your speed. At a given point in time, you're calculating your instantaneous velocity or speed. The question may ask, find your instantaneous speed at t equals 3 seconds. So we're going to see what happens if we try that. So from the problem, we know the change in time is 0 to 5.5 seconds, which gives us a delta t, or change in time, of 5.5 seconds. We know the change in distance is 10 to 35 meters, which is a delta d of 25 meters. So we're going to use these two numbers and plug them into equation to find out the average velocity during the journey, which is delta d divided by delta t, which gives us 25 meters divided by 5.5 seconds, which comes out to 50 over 11 meters per second. Recall that the problem said the position of the car changed at a constant rate. So when it asks you to find the instantaneous speed, that's a little bit of a trick question, and we'll see why eventually. The instantaneous speed at any time t for the journey is always going to be 50 divided by 11 meters per second. If the object is not accelerating at all, the instantaneous speed is always the average speed for the entire journey. So we're going to go on and show you a few equations and the derivatives. Here we have the function of distance. So d of t equals 50 over 11 times t. The derivative of the distance function is the speed, v of t. And this is equal to 50 divided by 11, which is a constant. So the derivative of v of t, a constant, is always the acceleration. And the acceleration is 0, because the derivative of a constant is always 0. There's no change in a constant. That last example was to show you the connection between derivatives and distance, velocity, and acceleration functions. In general, if you know one of them, you can easily find all the corresponding ones. This concludes the basic derivation of polynomials. The next lessons will be on exponential functions, in which we will also teach you the product rule and the quotient rule. So stay tuned for exponential functions.